Alright, here we go. You can see my mouse, great. Alright, so I want to take you through this project, the AIMS project, Antarctica Infrastructure Modernization for Science. So it was at McMurdo Station, Antarctica, and it was a contractor-led design-build project with many stakeholders. So the National Science Foundation has this polar program, United States Antarctic program, and there's a Antarctic support contract that's run through that. I kind of wanted to show you this, take you through this McKinsey presentation method, business consulting firm, and show you this sort of situation, complication, resolution. So, where we I'll show you this sort of the context, the situation, the complication, and sort of the energy efficiency measures we're kind of going through to fix it. So the stable area, they were kind of like just add a building, so there's many buildings on this campus, and for every new need they had, they would just sort of add a building. But they've had energy problems, running out of diesel fuel to power generators in the winter, and then so so I'll sort of go show you this resolution, take you through this sort of net zero journey they're on. So and the whole purpose of this is really to invest into the science station and the U.S. presence down in Antarctica. So all the stakeholders here, again, starts with the NSF and the polar programs, and then all the scientists and staff that work there, and the sort of the site and existing the existing base, and that creates all that information in the design process creates this sort of feedback loop where we kind of iterate the design and sort of come up with the best thing. So there's design of record, we'll kind of get in that, and then architecture record, and then the major contractor, steel erector, Southern Spear, and then Parsons was the general contractor. Leidos holds the main prime contract under the Antarctic support contract. So many people involved here in a very extreme environment. So you can see here, Antarctica is the highest, driest, coldest, windiest, emptiest continent on Earth. This is at Leidos office in Centennial, Colorado. And you can see how big Antarctica is compared to the United States. And this is Scott Discovery Hut. It's right next to the old naval base and the current base here. You can see Observation Hill here. And I'll kind of get into, you always can see Observation Hill from like pretty much wherever you are. And you can kind of see this volcanic dust that exists there. This was taken during the summer, probably, or spring. Which is the opposite of our North American summer. So you can kind of see how big the base is. This is Observation Hill. I think it's an extinct volcano. Then across the bay, you can see maybe even further than this is the Royal Society mountain range, and you can kind of see this is like a row of lodging. And some extraneous buildings around, some of which are storage buildings that are not conditioned, so I think they're going to phase some buildings out. You can kind of see Observation Hill here, and then McMurdo base here, and then this is New Zealand base, so you can kind of see how much larger McMurdo Station is than probably your average, quote, Antarctica science station. And then this is Discovery Point over here, and this is Winter Quarters Bay where they dock the ships. So you can kind of see Ross Island here, and the Ross Ice Shelf here, and Palmer Peninsula is another base, and then out sort of close to South America, and then this is the South Pole here. So a lot of teams go through the McMurdo Station, get ready to go to the South Pole or go anywhere in the backcountry of Antarctica. So yeah, this Ames project is a large budget project for using congressional money to improve the polar programs of the National Science Foundation, really improve the make it a nice place to work, and just maintain world-class science program down there. So a lot of the goals here are to improve efficiency, improve logistics between buildings, reduce operational costs, and just like try to stay within a budget and maintain the U.S. stature in the research community down there. So we were kind of given this master plan here, where you kind of have central services, lodging, fire, medical, recreational lounge, trades, and field science support here, and then like usually like a VOC, vehicle maintenance building up here. So and that's kind of what we kept. This is sort of like an early diagram of the fire station, medical, the gym, and the lounges here, and then like a warehouse, and then dining kitchen up here, sort of to replace Big Blue. New lodging building here, field science services, a concourse to load and stage vehicles, and then trades and a warehouse for them. So this was kind of the I shouldn't say A phase of the Ames project, where they're probably going to build this lodging building first. I think they got kind of shut down for COVID, and didn't have anyone on the island come new to the ice down there, and so that kind of is where this project stopped for me. But this would be central services. I think they'll probably build that first, and then it's built in a way where they could build this next to Big Blue, and then phase out Big Blue, and then build the new ops center and field science services and trades. This is their existing laboratories here. Those will stay, the Cray laboratories, and this is lodging buildings, and this will be a new lodging building here. Yeah, and then this is be a new fire station down here. So yeah, I guess total program, you're looking at about 250,000 square feet, and approximately like 250 million in building cost. So you're looking at large budget, large square footages on the probably the largest on the continent. So this would be like where a boat is. They would take they would unload everything, come in, and come build this new road here to access this service yard here. You come through as a loop, or you come through, drop off new scientists, people who are just getting here, and stage them through orientation. And this is where the kitchen is, and then there's a warehouse back here. So in the future, you could wake up here in lodging, go to rec or ops building, and then walk through to central services, field science supported trades, and not have to go outside. So that's something they're looking to do. So you can kind of see, I think this is the Big Blue building right here, and this is like a boat, and then the ice dock, and then the which they put dirt on top of frozen ice, and then here's I think that maybe it's right here, that bridge that has a weight limit. So you have the sort of filtering everything through the sides that fit on the boat to get over the bridge, and then I think we're building central services right about here. So central services again, VOC over here, a new lodging building. This is that recreational ops building, trades and field science services. So, and then you can kind of see this is all sort of the central services sort of nods to it, has a gesture towards the old Discovery Scott hut. right there. So, and again, I think they're trying to increase it. You'll see that we're trying to increase energy efficiency, but also to take advantage of this wind. They have a wind farm that they're sharing with Scott based in New Zealand there. They hope to expand that and rely more on wind power than diesel fuel. So we'll get into that here in a minute. And yeah, there's a 1972 shot of McMurdo Station. You can see actually it was actually never intended to be a permanent station. Then it was a naval base, and then it was converted to a science station, I think, ever since I guess 1957, this International Geographical Year. You can kind of see the sort of texture of the existing site, where they have a lot of lay down yards, like containers for waste storage. This would be like a row of lodging and big blue here, and I think some of these store water and diesel fuel, and yeah, so you can kind of see like how many buildings there are there. This is that Scott Discovery Hut, built around 1900. Still there today, preserved really well in the dry, cold climate. You can kind of see the existing base here. So this was the design build project, just sort of fast tracked, where we had a foundation exterior package, structural package, that include a lot of precast elements, and steel that could be often the same sizes, so you have this sort of civil foundation, shell, and core, and then we had a second package was interiors, more detailing. So it was a quick production schedule, lots of consultant coordination, and we're all thinking all this time that we have to ship from California to New Zealand and then to McMurdo Station, Antarctica. So you start talking to reps, and they're like, "We can't get this to Antarctica," and you're like, "Don't worry, you just have to get it to California, and they'll ship it." So we kind of went through several sort of design iterations, and we were working directly with the contractor to get, use our Revit models for cost estimation, and really sort of try to zero in on this price. And again, I think I explained this sort of feedback loop that we'd have with the existing, the scientists and the existing conditions and the staff there, and trying to make their, wherever they work, better. And sort of, as architect of record, we sort of boil this all down to something that's really buildable. So Oz Architects had this, master plan concept, and we were sort of working, and that came in over budget, so we had to kind of work with the contractor and work with the client to sort of get this price down, and deal with all the sort of extreme, extremities, or extreme environment that you have in Antarctica. So we kind of had this like contractor version where everything's more like straight, easier to build, and which you can kind of see, you still see Observation Hill here, pretty much the same massing as Oz Architects here had, in the same master plan that we're using. This was VOC up here, and so you can kind of see some a large entry point where the scientists would come in, new staff members. There's me with sort of that early iteration. We hung stuff up in the office. Don't miss the boat. So everything was taken down there on a boat, like this ocean giant here. So we had to be sort of cognizant of that, and the sizing of structural members and things like that. So a boat would get here, unload, come over this bridge, and then they would start to build You can sort of see buildings like this is the Chapel of the Snow, Big Blue, and then you can kind of see Winter Quarters Bay here. So they have to bring in an icebreaker first, and then they can bring in the big cargo ship, which would come from California to New Zealand to McMurdo Station, and then if they would also supply through that the South Pole. So we're talking about a lot of I think they call it Operation Deep Freeze, doing this whole around the Earth sort of shipment, and they can come a different way to get to the Palmer Station. So most tourists would come this way, and then not many people actually go to the actual South Pole when they go to Antarctica. So it's kind of a fascinating piece of information of logistics, sort of the macro logistics. And then you can sort of see here the McMurdo Station here and South Pole Station here. And then these are all the potential field research locations that scientists have to go out to. It's a very extreme environment down there. So, and the ground is pretty much frozen all year long, so you'll kind of see that right now they have all these utilities running above ground, these Arctic sleeves, and part of the updates is to run some of these underground, just make it more easily accessible and be able to repair easier. Kind of see these existing Utilidor, and then sort of this analysis of where we would have new utilities, new buildings, and sort of the existing sort of choppy utility plan to this one where it has like a sort of Utilidor mega loop here. So you can kind of see on where the Utilidor would go as of right now, providing underground access. You can see how large it is compared to a person. So it would really give people access to come and work on these things even in the winter. This is sort of that just add a building sort of mentality, just add lay down room or containers, which is no fault to anyone. It's just kind of the organic evolution of things, and then finding out that that's not the best way to do things. So they sort of are figuring out how to phase out buildings and which ones that they'll sort of phase out first and tear down first, and then I think the blue buildings right now are optional, and the yellow ones are as well. But they might. This is where VIOC is going. I think these buildings are current unconditioned storage. And then these are kind of some existing buildings. This is like the coffee hut, which is a pretty intimate space, and then a proposed new coffee, an additional coffee space and central services. Some buildings definitely be saved, like Chapel of the Snows. You can kind of see here they have like all these quirky names for things called like Derelict Junction, and you can kind of see these lodging buildings here, and here, and a frozen food warehouse here. So new proposed lodging building, pretty simple. Definitely a panelized design, where each window is inside one panel, pretty much one window per room here. You kind of see where you had lodging facility, or this would be a lounge. So they have their own kitchenette. They could throw parties, and this would be like a proposed room with special circadian lighting that would sort of help people with the 24 hours of darkness, sort of adjust to life down there. And this would be like a the hallway. Restrooms are over here, lodging's over here, or the lounge is over there. So you can kind of see other sort of buildings where they may not have a lot of storage space, so we're providing like more storage space. And this is just big blue, sort of the central hub, but we're just gonna pretty much keep a lot of the same concepts, just really update everything. Same with the current fire station. So same with the trades building. Again, this is like a lot of storage here. And then they have to ship fuel down there to run diesel generators to have power in the winter and just keep everything running down there. So a lot of the work that we're doing here is to hopefully reduce the fuel usage at least by 24%, hopefully more. But we're dealing with a pretty extreme environment, so I think we, with potential to use more combined heat and power generation, they can start to really reduce the amount of diesel fuel that they have to burn down there. So fuel is delivered once a year, and they say the diesel plant makes about 2 megawatts. And electric consumption granted, that was 2002, was 15,000 megawatts per hours. So they're consuming 1.3 gallons per year, and that includes water, water desalination, and heat and power. So hopefully we can save them a lot more money on diesel fuel, especially since that's a rising cost nowadays. And then they're hoping to add on and to this wind farm that's shared with the New Zealand Scott base. So they hope to expand that some more. And just to show you sort of, this extreme environment, we did use a lot of stainless steel. This is the Belgian station that has the sort of it's very similar sort of exterior envelope where they have the stainless steel, and then basically just a large amount rigid insulation, and then a vapor barrier. So they have this inner wall here, this wood wall here, I think they would that is probably considered the vapor barrier here, and they probably have some sort of sealant on the inside. But they have an outer skin, a whole lot of insulation, and then a vapor barrier on the inside. So we sort of had a early mock-up here in the office, and the idea is to just get a lot of this, like a whole roll of steel, and then like a 4-foot roll, and then just fold in the sides and then use that as a 4-foot panel. So so we're dealing with a lot of insulation here, R72 roof, R60 walls, and the 2-foot geofoam underneath it. So you can just tell we're dealing with a lot of insulation here, thick walls, and thick roof assembly. So I think this roof assembly would be a standing seam roof panel over a roof SIP panel. So and we did lots of energy models to figure out kind of what's the this would be like code, and this would be sort of what's the right size of wall. Ended up being that R60. And we were working with a manufacturer that that does things, that has these cam locks when they join together, creating a tight seal. They do things like have one piece that's foamed through at the corners, and we tried to put windows inside of a panel just to decrease leaks and air gaps and things like that. So you can just see here with the SIP design, we had a lot of thick walls, and then figuring out how to sort of attach that to a steel superstructure, and then you have these sort of precast steel. How are they connected at the joints here? Even something simple as a vertical lift door, you really have to design, and it's more like a wall panel that lifts up here. So really just trying to eliminate all thermal bridging. So yeah, I think this was sort of we have that superstructure steel, interior finish, vapor barrier. Sometimes those can be very similar, like paint. A thermal barrier, which is all the insulation. Air barrier, which would be the skin of the panel, and then also that is the exterior paneling, and then we have doors and windows and curtain wall in certain spots. That's triple paned, and triple paned high performance windows, so with insulated glass units. So some part of our standardization for shipping and sort of taking this original plan and making something a little bit more straighter, a little bit more easier to build, but trying to keep the essence of the building. So we had a 32 by 32 foot grid, just for standardization. And then within that grid, each grid, or in between each grid, really has 7 or 8 panels here, sometimes 8. But you can see they're all, we sort of had these what we call these sort of ice chisel shaped pieces that sort of kind of represent like an ice shelf sort of calving off, and sort of kind of represent the sort of take the context and make the building sort of make sense. But so we had all these kind of crazy shapes. Always ran through this sort of 4 foot grid. So you kind of see here we'd have like a construction document for this. We'd have a sort of 3D axon, and then we'd show it in elevation here and here. You kind of see the grid lines here, and then we used Dynamo to sort of take that massing shape and then cut it up into that 4 foot grid, and then take each panel and then take each panel here and then flatten it out so it'd be able to cut and ready for the fabricator. So this is that Dynamo screenshot, but this is kind of like how we took this complex geometry and made it into something, it's pretty simple, and it's all marked of which panels which, and something that the fabricator can make. So did that for a couple, I think there were 5 chisels total. And some of the early work that was done, the prevailing winds you can kind of see here from the east and south, and you kind of see this in the snow modeling. They did it from 2 directions, and we sort of adjusted the grades that we had around the building here to stop the snow from building up with the red areas. And but we pretty much kept, again, like the same master plan, same general concept in massing. So these were done at CSU at their wind tunnel. So you kind of see this base massing here: central services, lodging buildings, the ops, field science services, and trades. So, and this is that existing Cray Labs here, the laboratory. So they would run, simulate snows, like a really bad snowstorm, and during winter. And this is kind of like what they came up with, and they document all this and give that to us, and we sort of can make adjustments according to that. So a lot of the larger buildings are built right on the permafrost, and then a lot of the smaller buildings are raised up so they don't melt the ground, but they're small enough so the snow will scour underneath it, because it's really dry, powdery snow, because it's just freezing all the time there. And that was something we did with this new lodging building was, have it up off the ground. But for the other buildings, we needed this permafrost protection, and we had energy modelers sort of model, again, to right size this geofoam insulation. It's basically 2 feet to protect the frozen earth underneath the building, and so we sort of ran a simulation, in the winter. Say the boiler room gets to 100 degrees, worst case scenario, does it melt the permafrost? And the answer is no, if you have that 2 feet. And then, so this would be a winter -30, and then in the summer it might be tops like 37 or 40 degrees. So again, but if it does get that hot in your boiler room, say it's really hot for some reason, does that cause anything to melt? And then again, no. So we sort of right sized it again. So you kind of see how this building kind of works with the grade, and we have that grid, and sort of the building sort of works with grade. And this is a warehouse here that can be open to the exterior to remain frozen, or they can heat it, either or. Kind of a cool thing. But this is the dining room and other offices up above. You kind of see there's a lot going on. There's a radome up here for weather observation. So energy efficiency was a big item for us, and the real, you're dealing with subarctic. I think it's climate zone 8. It's like the most severe, and you have 12,600 heating degree days, which is a lot of demand on your heating systems. So yeah, you have a relatively high UI still, but believe it or not, I think that is actually energy efficient for Antarctica. But there's not a lot of data, and sometimes the buildings don't perform as well as they think they will. So really hoping here that we can track a lot of this new data, and they can work on lowering their EUI after post occupancy. But again, so you're pretty much your heat loads. Usually you have like a peak in the summer and peak in the winter, but your energy loads, right? So, but this is pretty much just year round, like freezing, so, or -30. So you have just pretty much steady. It's that 12,000 heating degree days. Yeah, we definitely have looked at lead equivalent and ASHRAE equivalencies on these, but we're not actually trying to get lead here. But we have done a lot of energy modeling and sort of made sure the building is energy efficient in the most sort of responsible way we can do that in this extreme environment. So and again, just to break down, your most of your heating load, or your energy load, is going to be used for space heating, and then equipment. This is like a multi-use building with offices and kitchens and things like that, and lighting, and then pumps and fans, and I think that's hot water, domestic hot water. So that's sort of where they are, kind of on their net zero journey. And again, this is sort of the inspirational we were using for that sort of chiseled face, sort of where the ice shelf sort of calves off into the sea. And we took a lot of the materials and things from Antarctica. Like if you look underneath the sea, there's actually a lot of different colors, and a lot of different diversity, and a lot of things to pull from, actually, in terms of BIO-PHILIC design and circadian design, and a lot of just sort of whether that that be sort of, you know, notes that you're taking from the site and the context and nature. So these are kind of the renderings of the largest building here on the continent, so the Central Services Building, where they, you know, this is sort of that prow where it kind of sticks out towards that Scott Discovery Hut, and then this would be like a cafe up here, offices up here. I think the executive directors and other executive suite is up here. Dining hall is all through here, and then this is another lounge, like a bar type of area down here. You can kind of see we had, you know, a panelized system and vents and all sorts of things in this facade here. But yeah, we sort of had these craggy shapes here, you know, trying to sort of mimic that ice shelf sort of iceberg, aesthetic. And then we're using this red color as like a safety color. And again, it is a science building, so there's like a radome up here with a satellite inside that dome, a satellite dish. Yeah. And this is that like main arrival point where when they sort of drop off new people, do orientation in the auditorium down here, coffee area above, offices, warehouses type things back here. Side is that weather observation deck here and here, and this is like a passenger terminal where they handle departing and arrival of passenger bags and things like that here. You can kind of see this is that concourse in between trades and field science services right there. And yeah, so early interior shots here. Auditorium where they do orientations and things for large groups. Like proposed coffee shop, dining area, lots of variations for groups or solo diners. Again, some early shots of the interior. Yeah, just a lot of structural coordination. You know, we're using precast panels and a steel megastructure here. Just a lot of coordination going up through with these buildings, because they have to withstand over 150 miles per hour winds. And again, you can kind of see the superstructure steel, and then the thick thermal insulation, the thermal envelope, if you will. Again, just some drawings used for documentation, like the auditorium. Pretty cool shots using Revit. Again, the auditorium. Okay, and then I just want to talk about vapor drive. So since it's so dry in Antarctica and it's so warm and humid on the inside, there's a large temperature difference between 70 degrees and 30 degrees, or negative 30 degrees. There's a lot of vapor drive, so it wants to go from 70 degrees outside, and eventually it would freeze and cause thermal expansion inside your wall or building, and that would be bad. So you have to create a vapor barrier to stop that. So another thing that we had to do is, you know, sort of right size the thickness here, is make sure your dew point is inside the wall, so wherever it wants to have condensation is actually inside the wall and not inside your building. And so here would be like a finished material, vapor barrier, insulation, and then the outer skin here. So that's one thing we always were trying to watch out for, is having this condensation point inside the insulation, so it doesn't happen. And yeah, you can kind of see these blue lines that we included in sections, details trying to explain where the vapor barrier would be, to stop that vapor drive, that moisture going from the inside to the outside of the building. And then again, detailing things just like simply like overlapping insulation to stop thermal bridging, or to essentially stop heat from escaping. And where you have a steel connection come through the outer skin, you do things like have a thermal break, and just simple detailing. So kind of just wanted to take you through sort of that big idea master plan down to through the design iterations down to the detail. So yeah, questions, please comment below, let me know what you think. And yeah, that's it. Just follow me on Instagram, Parker Williams Architect. Have a lot of stuff on there. So thanks for your time, and talk to you again.